Normal versus forced, you can see. Pulmonary function test. Now we're getting into the pulmonary function test. Spirometry, that's what we did. Spirometry, that's what we did in the lab. Measures lung volumes and capacities. You look at restrictive or disruptive lung orders. Tidal volume, know these, the amount of air expired on quiet breathing. Expiratory reserve, amount of air that can be forced out after. Inspiratory reserve is the amount of air that can be forced in after tidal volume. Residual volume is the amount of air left in the lungs after maximum expiration. Again, that's a calculation, can only be measured on autopsy. Vital capacity is the maximum amount of air that can be moved forcefully exhaled after a forceful or maximum inhalation. So that's as much as you can move. Total lung capacity is the amount of gas in the lungs after a maximum inspiration. Inspiratory capacity is the amount of gas that can be inspired after normal expiration. Functional residual capacity is the amount of gas left in the lungs after a normal expiration. Lung volume and capacity, vital capacity, these are in your book. Inspiratory reserve plus expiratory. Functional residual, you need to know these. These are the second part of chapter 13 in your lab. Here is a spirogram. You did this in lab. Take a look at this. Restrictive, lung tissue is damaged, vital capacity is reduced, but forced expiration is normal. Obstructive, lung tissue is normal, vital capacity is normal, but forced expiration is reduced. Asthma. Restrictive, you have pulmonary fibrosis and emphysema. In emphysema, the lung tissue is damaged, your alveoli come together and form like one big sac, and you lose your surface area, you lose the ability to transfer oxygen into the capillaries. FEV is your forced expiratory volume. You have FEV 1, 2, and 3. 1, 2, and 3 are seconds, and it shows just how you're able to move air in and out. Asthma, shortness of breath caused by inflammation of the bronchioles and constriction of the bronchioles. Allergic asthma by allergens, by cold or dry air. Reversible. You see the people with albuterol with little bronchi misters, and I'm just drawing a blank, I'm sorry. Obstructive pulmonary disease, it's inflammation of the airways and alveolar destruction. Emphysema, this is what happens with smoking. Accelerated decline in the forced values. Inflammation involves macrophages, neutrophils, T cells. Mucus production, inflammation triggered by smoking. Most people with COPD smoke. Fifth leading cause of death, no cure. Emphysema is a destruction of the alveoli. It reduces the surface area. Smoking, again, it triggers it. Pulmonary fibrosis, you lose the elasticity. Black lung in miners. Coal miners, not miners as in young people. Gas exchange in the lungs can be measured. We're not going to go into that. We're not going to go through Dalton's law. Partial pressure, Boyle's law, and that we're not going into. Relation between alveoli and capillaries, they wrap around. Use oxygen measurement, you use an electrode. It measures the oxygen in the plasma, not in the red cells. Partial pressure, pulmonary circulation, we talked about. The pressure is much lower in the pulmonary arteries than it is in the other systemic arteries.
Fresh air entering the lung carries oxygen with a PO2 of 160. The presence of moisture in the lung results in reduction of the PO2 to 104.
We're not going to go through that, at least not part of this. Disorders caused by the high partial pressure of gas. You're looking at the bends from sea divers. As they are deep, the pressure forces nitrogen into the tissues and into the plasma. If they come up too fast, the nitrogen cannot disperse. It forms bubbles and in the blood, and it can be extremely dangerous. Nitrogen narcosis is inhaled under pressure. Dizziness, drowsiness. It could be something called a rapture of the deep too, where they get confused, and many times rather than diving toward the surface, they dive deeper and sometimes drown. Compression sickness. A diver comes to the surface too fast, nitrogen bubbles form in the blood, block the vessels. 2 tracks, the voluntary from the cerebral cortex. We are not going to go into this in the lab. Hemoglobin. Hemoglobin and oxygen transport. This is in chapter 14. We're looking at the components of blood we've already talked about. Blood values in diagnosis we talked about in the lab. The plasma contains many different, as I said, we do between my lab and reference labs, we probably do over 1,000 different tests on the blood and body fluids for different types of diseases. Earlier in the semester we talked about the difference between normal range, normal values versus average. And in the different diseases. Hemoglobin carries the oxygen. Oxyhemoglobin is iron reduced, combined with O2. Methemoglobin is oxidized, it can't bind. Carboxyhemoglobin is found with carbon monoxide poisoning. Saturation is normally about 97%. Anemia is below normal hemoglobin. Polycythemia is above normal. Polycythemia is a time when we still bleed people. Erythropoietin is made in the kidneys, stimulates RBC production. Loading and unloading in the lungs, we've just gone through that. Oxygen dissociation, some oxygens remain in the veins, oxygen reserve. pH. pH changes the affinity for hemoglobin for O2. This ensures muscles get more O2 when exercising. Affinity decreases at a lower pH and increases at a higher pH. The Bohr effect. At a lower pH, you're using energy, you're producing more carbon dioxide. Carbon dioxide combines in the blood to form carbonic acid, drops the pH a little bit. This allows more oxygen to be released. Hemoglobin affinity for O2 is decreased at increased temperatures. And then you have our energy from anaerobic, increased 2,3-DPG. 2,3, it increases oxygen unloading. It decreases again the 2,3-DPG, like people that are training at high altitude, people that live in Nepal, up in the Himalayas. This increases the oxygen unloading. It allows whatever oxygen has gotten into the lungs and into the blood to unload into the tissues easier. Fetal hemoglobin, it's different. It binds a different affinity, so it transfers more oxygen to the fetus. Sickle cell is a different type of hemoglobin, an S hemoglobin, deoxygenated. It hinders, the cells are different, it hinders their ability to pass into the vessels. One thing with sickle cell, it does prevent or minimize the effect of some types of malaria. Here's a regular red cell and a sickle cell. Thalassemia and Mediterranean. Again, defective hemoglobins that resist malaria. Myoglobin stores oxygen in the tissues. Carbon dioxide diffuses. I think we've been through this. Carbonic anhydrase we talked about. Bicarbonate forms dissociation into bicarbonate and hydrogen ions. You get a chloride shift. The Bohr affects, again, the affinity of O2. Reverse chloride shifts. Acid-base balance of the blood we've already gone through in the earlier chapters. You talked about, again, the carbon dioxide and the bicarbonate buffer system. And I think that's all we're going to go through. Exercise at a high altitude on respiratory function. Faster breathing to match oxygen utilization is hypernia. Neurogenic and normal mechanisms control that. Humoral mechanisms, we're not going to go through this. I'll just let you take a look at it. Sorry, going to be a little bit fast. I think you can stop it and look at it. And that's it for chapter 14. So I'll try to get this mixed and out to you. Have a good evening.